So in today's lecture, we will discuss about the principle of signal conversion. As in our previous lecture, we have already discussed the various issues which are related to the implementation of digital control. In this particular lecture, we will see that how an analog signal is converted into a digital signal. As it is been discussed in previous lectures also, that the digital control system, or in digital control system, it is the signal which is processed digitally. It is not the complete loop which is digital in nature. Our real-time parameters or processes like temperature, pressure, flow level, etc. So from these processes, we acquire the analog signals, and these analog signals are processed digitally through computer or microcontroller or microprocessor. And based on the control algorithm, the control signal is generated, and this control signal is also digital signal, and this signal is then converted back into analog because the real time process will not understand the digital signal or digital information. So let us start with the lecture. So let us come to analog to digital conversion. The analog signal is converted into digital signal by using the device which is known as A to D converter, analog to digital converter, right? So A to D converters, what they do, they convert or transform or translate the analog signals which are acquired from the real world or real-time processes like temperature or pressure or voltage, current, or anything like that. And so they convert such type of signals into the digital representation. And digital representation is basically the binary representation of the analog signal. Then when once we have that digital representation of the analog signal, these signals are basically processed digitally through a computer or microcontroller, and according to the algorithm stored in the microcontroller or computer, the output is computed, and this output is computed as well as it is transmitted and stored. Storage is done so that it can be used for further analysis. Now, A to D converter, what it does, it samples an analog waveform at some uniform time intervals and assigns a digital value to each sample. So that means one of the uh, objective of A to D converter is to sample the analog signals, and the sampling that is done is the uniform sampling. So uniform sampling is acquiring the information at some specific, like if you have some analog signal like this, so if you acquire the information of this analog signal at some specific uh, intervals. So if the time period between two successive intervals is same, so we call this as the uniform sampling. Otherwise, non-uniform sampling, in, or you can say in non-uniform sampling, the this, the time period between the successive samples may vary like this. So now, when the A to D converter converts the analog signal into digital signal, it not only gives you a discrete output, but it gives you a binary representation of that analog signal or those samples basically, right? So that means A to D converter, what it does, it does two processes. One is known as sampling and second is known as quantization. Sampling is a process of acquiring the data from the analog signal at specific time points, basically, or instants, you can say specific instants, so that data at a specific instant will become a sample. In this way we may have a number of samples of an analog signal. Similarly, it quantizes the samples. Now what is quantization we will see in the next slide. Now, from this block diagram representation, you can understand how this digital output is uh, obtained from an analog signal, or you can say how this A to D converter assigns a digital value to every analog sample. So this is the formula for that. So n bit resolution, that means if let us say if an A to D converter is a 2 bit is of 2-bit resolution, that means there will be four data samples or four quantization levels. So in this way we can get the digital output of any analog signal. Okay, so the analog input, basically this is the real time signal which is being acquired using transducers or sensors. It is compared with some reference input and given to A to D converter, and based on this particular formula the digital output is obtained. Now in this slide we will discuss about the operation of an A to D converter, basically, as it is mentioned earlier also that an A to D converter samples an analog signal. So first of all, let us consider an analog signal as shown in this diagram here. So the first process which is done by an A to D converter is sampling. So as you can see here, there are five samples in this particular of this particular analog signal. So these samples have been acquired at different instants. Now we have these many samples here. So each sample will have some magnitude. So the magnitude or amplitude will be as it is taken here, here, this one, and then let us say this one. Okay, so there are 5 to 6 samples approximately. So this particular sample has not been considered here. So fine, doesn't matter. So we have these many samples. Every sample will have an amplitude. So amplitude will be as it is, right? Then after sampling, the quantization is basically done. So as you can see here in this particular diagram, these are the quantized samples. Now what is quantization? Quantization, in very basic statement, if you want to understand, quantization is basically rounding off of a fractional value. For example, if you have a sample, let us say this particular sample, because it is almost near to 2, if the value is, let us say, 1.75, so we'll round off this particular to 2.0. If the value, and in this case if you see the value of this sample, the amplitude of this sample is almost 2 point, let us say 2.30, for example. So we have again rounded off this particular sample to 2.00, and here in this case if you see the value of the amplitude is almost 2.9, for example, like this. So we have rounded off this sample to 3. So this rounding off of a sample is the quantization process, so that we can get the discrete values of the sample magnitude. Instead of having the fractional value, we have now the discrete value, right? And then the final step or final work of an A to D converter is to assign a binary code to every sample. Now, in this quantized diagram, if you see, the magnitude or the amplitude of zeroth sample is 2, first sample is 2, second sample is this 3, then this sample is 1, and then fourth sample is uh, 0. So the binary equivalent of 2 is 1 0. Similarly, the zero sample is 1 0. First sample is this. Then second, the binary equivalent of 3 is 1 1. And 3, this one, this is third sample. So it is 1. So it is 0 1 here, binary equivalent. And this one is 0. So the binary equivalent is 0 0 in this case, right? So this is how the conversion takes place from analog to digital. Then once we have this digital representation, it is transmitted to a distance, received by some receiver, then it is decoded. After decoding, the uh, tough task is to get the exact reconstruction of the sample signal, right? So this block diagram here will explain all these four processes or the operation which is performed by an A to D converter. As you can see, firstly we have the continuous time, continuous amplitude signal. So this is the continuous time and continuous amplitude signal, means the analog signal. Okay, so here we have the analog signal, right? So we feed the signal to sampler. The first step is sampling. So after sampling, we get a discrete time but continuous amplitude signal. Now, what is discrete time and continuous amplitude signal? That samples are at some discrete instance, right? So that is why it is discrete in time, but the amplitude of each sample will be as it is. It is not rounded off. These may be the fractional values. These are not some discrete values, right? So to get the discrete values of the amplitude of each sample, we need to quantize those samples. So this is done by quantizer. Now after quantization of the samples, we get discrete time, discrete amplitude signal, right? Now here, this is also not the digital um, signal. To get the digital signal or binary representation of the given analog and its samples, we need to use the encoder. So this is done by encoder. Now encoder encodes those uh, analog samples into equivalent digital binary codes basically. So finally we get the digital representation of the given analog signal. Now let us understand about digital to analog conversion. Now, because if you see a block diagram representation, so we have a digital controller here. So this digital controller could be a microcontroller, it could be a computer. Okay, so this has to be interfaced with the real world using two devices which we call as A to D converter and D to A converter. So here we get the control output which is represented or denoted by UK, where K is the samples. So from D to A converter we get some uh, analog representation of this particular control signal. It is given to the final control element, and then we have the plant. So plant has output, we have fed back this one, measured feedback element, and here we have the comparison. Either the comparison is done here or comparison can be done here also. Reference can be taken here or reference can be taken at this point. So doesn't matter. Okay. So error will be converted into A to D converter. That this is the only difference, right? Plus minus. So now this D to A converter is used so that the digital output of the digital controller can be used to operate the plant or manipulate the process variables, because the plant in real time will not understand ones and zeros, right? So, the real world signals such as temperature, pressure, sound, or images are routinely converted to a digital representation that can be easily processed in modern digital systems. So, this is what we have been talking about this, concept. Now, in many systems, the digital information must be converted back to an analog form to perform some real world functions. Now, the circuits which convert the digital signal into analog signal are known as digital to analog converters, right? The best examples are your loudspeakers, video displays, motors, mechanical servos, radio frequency transmitters, temperature controls, etc. So this is the block diagram representation, or a diagrammatic representation of D to A converter. So we feed binary inputs to D to A converter and we get some digital signal output based on its internal working. The analog signals are received. Analog representation of the given samples is received, right? So it depends upon the internal structure of the D to A converter. Okay, so we have two types of methods or structures which are used to have the digital to analog converter. The one is weighted resistor type, and the second is R2R ladder network, right? These two methods are used to convert the digital signal into analog signal. So a D2A converter, what it does, it receives the digital signals, decode those digital signals, and convert these ones and zeros to the discrete time signals, right? So these discrete time information or signals are given to zero order hold. So this is a hold circuit basically. So this hold circuit is used to convert the discrete time signals to the analog signals. So a D2A converter performs two functions basically. The first is it converts the binary representation to the discrete time representation. Then it converts those discrete time samples to the analog form. As you can see here, the sampled signal. So this is the discrete time signal, right? So this is quantized as well as discrete in time. It is obtained by converting the digital representation into the discrete time by a decoder. Then using the hold circuitry, specifically zero order hold, so we have this analog represent. You can see this is a continuous. So how this work, basically the hold circuit will hold the signal till the level changes. Okay, till there is a change in the level basically, as you can see here. So it starts from 2, so till next sample is arrived, so the output will be kept on 2, right here, like this. So when the next sample has arrived at 1, so it will see that it is again 2, so it will keep on continue here, right? So at sample 2, it will see that the level has changed. Now the level has reached to 3, so it will immediately step up to 3 value and then keep on continuing like this, right? And then it will see that at third point the output, the magnitude has changed. Okay, so it will come down to this magnitude, and then again at sample 4 it is 0. So till sample 4 it will keep on continue with the same magnitude, and as soon as the sample fourth is received. So we have this ripple. So it is something like this. Okay, so this is the basically analog representation of the given analog signal, but this is not the exact representation because of the hold circuitry we use. But there is a reason to use zero order hold. Now, what is zero order? Zero order is basically the order of the transfer function of this zero order hold this hold circuitry, right? So the decoder, what decoder does, it maps the digital or binary representation to the discrete values, right? Quantized value basically. So now the second is the holding basically the value at a particular sample and then change the value when the sample receives. Okay, when the sample magnitude changes, right? So this is done by zero order hold circuitry. So here the zero order refers to the zero order polynomial used to extrapolate between the sample. Basically, we when we get the transfer function of this circuitry, so it is of that particular order. Okay, so we have first order, second order, like this. We have the hold circuitries. So the purpose of hold circuit is to hold the sample till the next level, next sample is obtained, and then it changes with the change in the amplitude of the sample. Otherwise it will remain as it is, right? Now you can see here in this particular diagram through an animation, as you can see this torch is putting some light. So light is an analog information, so it is putting some light on this LDR. LDR is light dependent resistor or light detecting resistor, you can say. So the output, and this is a sensor and transducer basically, right? LDR. So what you can see, the output of this LDR is fed to A to D converter, and A to D converter is converting this light information to the binary equivalent, right? Similarly, in this example, you can see this is the mic and these are the speakers. So mic is capturing the voice, converting that into some binary equivalents using A to D converter. We have digital signal processor with us. It is processing um, the information as required, and then it is being stored also in the memory. Then DSP is sending these ones and zeros to D2A converter. D2A converter is converting this information back to the analog, and the output is obtained through speakers, right? So in this lecture, we have understood how this uh, conversion takes place. What are all the steps which are used to convert an analog signal into digital signal. So this was all about today's lecture, guys, and thank you so much.